Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today I want to discuss about engineering typology subject. So in this subject already we have learned the friction and wear and lubrication topics, and also we have discussed on the various questions and definition and terminology. But in this session, so I have selected some specific topics. The selected topics 4. Already 1, 2, 3 is over. In this 4, I have taken corrosion topics, dry corrosion and wet corrosion topics. So we will discuss in this session on dry corrosion and wet corrosion. So in this topic already we have studied about corrosion definition and then types of corrosion and prevention, how to prevent the corrosion also we have seen. But in this, in selective topics, so again we will discuss about these two, the dry corrosion and wet corrosion, and other definitions if any missing. So dry corrosion. So as per definition, dry corrosion also known as chemical corrosion. So occurs in the absence of a liquid electrolyte. So it typically happens in gaseous environments. So dry corrosion is known as chemical reaction. Whenever the chemical reaction is occurred, so there is a corrosion between the atmospheric air gases and then metal surface. So that is called as dry corrosion. So mechanism is involves the direct chemical reactions between the metal and the gases in the environment. So the common reactions include oxidation, sulfidation, and halogenation. So these are the main reactions included in this dry corrosion mechanism. The conditions are this typically occurs at high temperatures, no presence of a liquid phase. So that is electrolyte, not required any electrolyte. So the examples: oxidation of metals at high temperatures in air or oxygen. So sulfidation in environments containing sulfur gases. So halogenation in the presence of halogen gases. Example chlorine. The products, the formation of solid corrosion products such as oxides, sulfides, and halides. So these are the formation of solid corrosion products. So these products can form a protective layer. So example, chromium oxide on stainless steel, or be non-protective. Example, iron oxide or on iron oxide and carbon steel. So these products can form a protective layer. So characteristics are usually uniform corrosion across the surface. The corrosion rate can be influenced by temperature, gas composition, and metal properties. So often forms a thin continuous film on the metal surface. These are the characteristics. So how to prevent? Use of high temperature alloys and coatings, environmental control to reduce exposure to reactive gases. So the application of protective oxide films, example aluminizing and chromizing. These are the application of protective oxide films. Next, wet corrosion. So as per definition of wet corrosion is also known as aqueous or electrochemical corrosion. Occurs in the presence of a liquid electrolyte, typically water. So the mechanism involves electrochemical reactions where metal atoms lose electrons. So oxidation and become metal ions. So they lose electrons, nothing but oxidation. The gain electrons is reduction. So whenever the metal atoms lose electrons, there is oxidation and it will become metal ions. They requires the presence of an electrolyte to facilitate ion and electron transfer. So electrolyte is required. The formation of anodic and cathodic regions on the metal surface. Next, conditions typically occurs at ambient or moderate temperatures. The presence of a liquid phase, so water or other electrolytes. Examples: rusting of iron in water, galvanic corrosion between dissimilar metals in an electrolyte, fitting corrosion in chloride containing environments. The products are the formation of hydrated corrosion products such as rust, iron oxide or hydroxide. Products can be loosely adherent and non-protective, leading to continuous corrosion. The characteristics are can be uniform or localized, fitting and curvaceous corrosion. The corrosion rate influenced by factors such as oxygen availability, pH value, and electrolyte composition and temperature. So involves electrochemical cells with anodic and cathodic areas. So the prevention is use of corrosion resistant materials and alloys. The application of protective coatings, paint or galvanization. Cathodic protection, sacrificial anodes, impressed current systems. The use of corrosion inhibitors in the electrolyte. The design considerations to minimize curvaceous and ensure proper drainage. Next, fitting corrosion. In this corrosion, it is a localized form of corrosion that results in a small but often deep fits on the surface of metal. So it can lead to significant damage and failure of structures, even if the overall metal loss is minimal. Material selection, alloy composition. Criteria: choose materials with alloying elements that enhance fitting resistance. Performance is alloys containing elements like chromium, molybdenum, and nitrogen. It is example stainless steels offer better resistance. The example for this alloy composition 316 stainless steel with molybdenum composition is more resistant to fitting than 304 stainless steel. So in this, the alloys are chromium and nitrogen. Microstructure. The criteria is materials with uniform and fine-grained microstructures are preferred. The performance is fine grains reduce the initiation sites for fits and provide better overall corrosion resistance. The surface condition. Criteria smooth, clean surfaces are less prone to pitting. The performance is polished surfaces reduce the number of curvaces and sites where fits can initiate. Next, environmental conditions. Chloride concentration. Criteria is use materials resistant to chloride induced fitting in environments with high chloride concentrations. Performance is materials with higher fitting resistance equivalent and numbers perform better. The examples are titanium and nickel based alloys in seawater environments. So based on the environmental conditions, so the chloride concentration that is one factor, and then pH value, the pH levels. So the criteria is consider the pH of the environment where the material will be used. So what is the pH of the environment you have to measure, and then where the material will be used. The performance in metals like aluminum are more prone to this fitting in acidic or alkaline environments. The temperature is higher temperatures can accelerate fitting corrosion. Select materials accordingly. The performance is high temperature resistance alloys perform better in hot environments. Next, design considerations. Avoid curvaceous and stagnant areas. So criteria is designed to minimize curvaceous, sharp corners, and areas where water can stagnate. The performance is designs that ensure proper drainage and fluid flow reduce the risk of fitting. Cathodic protection. So criteria is use cathodic protection in critical applications to prevent fitting. The performance is sacrificial anodes or impressed current systems can protect susceptible metals. Next, protective coatings and treatments. The coatings criteria is apply coatings that acts as barriers to prevent exposure to corrosive environments. The performance high quality coatings like epoxy, polyurethane, or metal plating. Example galvanization provide effective protection. The surface treatments are criteria use treatments like passivation to enhance the natural oxide layer. So in the surface treatments, the performance is treatments such as polishing improve the resistance of stainless steels to fitting. Next, maintenance and monitoring. The regular inspections. Criteria is schedule regular inspections to detect early signs of fitting. The performance is early detection allows for timely maintenance and reduces the risk of catastrophic failure. The monitoring techniques are used techniques like electrochemical noise analysis and fit depth measurement. The performance is advanced monitoring can provide real-time data on fitting progression. Next, corrosion inhibitors. In this, the chemical inhibitors, the criteria is use corrosion inhibitors in the environment to mitigate the fitting. The performance inhibitors like molybdates and nitrates can reduce the aggressiveness of chloride ions. Next, anodic protection. So it is a corrosion control method that involves the making a metal structure and the anode of an electrochemical cell to maintain it in a passive state. The advantages are effective for passive metals. The benefit is highly effective for metals that form a stable passive oxide layer. Example stainless steel or titanium. Explanation anodic protection maintains the metal in a passive state, reducing the corrosive rates significantly. The low current requirements. The benefit is requires less electrical current compared to cathodic protection for maintaining passivity. So anodic protection method, it requires a very less amount of current. Once passivation is achieved, only a small current is needed to maintain the passive field. The protection in aggressive environments, the benefit is effective in a highly aggressive environments where other protection methods may fail. So can protect metals in environments with high SDT, high temperatures and high chloride concentrations. Next, cost effective for large structures. The benefit is more cost effective for protecting large structures like storage tanks and pipelines. The explanation, lower current requirements translate to reduced energy cost over time. So the long-term protection is, the benefit is provides long-term protection with minimal maintenance once the system is properly set up. Stable passive film, the explanation requires the stable passive film requires less frequent monitoring and adjustments. Next, disadvantage is also there. There is complexity of control systems. Main drawback is requires sophisticated control systems to maintain the correct potential. The precise control of the anodic potential is critical to avoid over or under protection. The limited to certain metals. Drawback is only applicable to metals that can form a passive oxide layer. Explanation, not effective for metals that do not readily passivate, such as carbon steel, without suitable alloying elements. So initial setup cost, high initial cost for installation and setup of the anodic protection system. Explanation requires investment in control equipment, power sources, and monitoring systems. Potential for passive layer breakdown. So main drawback, risk of passive layer breakdown under fluctuating environmental conditions. The changes in temperature, pH value, chloride concentration can disturb the passive layer leading to localized corrosion. Limited to use in non-stationary structures, not suitable for moving transportable structures. Anodic protection systems are designed for stationary setups where constant monitoring and controls are feasible. So these are the topics related to the corrosion. This dry corrosion, wet corrosion, and protective methods we have seen, and then anodic protection and cathode protection, and maintenance and monitoring protective coatings and treatments, design consultations also we have seen. So these are the references taken for this topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.